How do we incorporate biocompatibility early in the plastic recommendation phase? This is one of the most frequently asked questions because I often hear, is this grade biocompatible? Or this grade is approved for medical since it is ISO 10993 certified. Or we cannot use this grade because the manufacturer has no ISO 10993. So this is, I would say, all of this is half knowledge because ISO 10993 doesn't mean approved for medical. And we will myth bust a little bit how biocompatibility actually works. So in this video, you're going to learn what biocompatibility really is, how one assesses biocompatibility, and what the ISO 10993 is, and how we apply all of this knowledge to plastic selection. So buckle up, it's going to be a hefty video. My name is Lucas Penigonda, and I've helped over 30 MedTech companies with plastic selection and sustainability. So let's dive into it. So let's start with the definition of biocompatibility. Biocompatibility, according to the ISO 10993-1, which is the biocompatibility norm for medical devices, defines biocompatibility the following. Biocompatibility is the ability of a medical device or material to perform as intended with an appropriate host response in a specific application. Meaning, biocompatibility is very much dependent on the contact type, on the invasiveness of the medical device, and the contact duration. That means that a material can be biocompatible in one scenario, but not in another. And this is exactly what I mean when I say, hey, can we use recycled materials in medical devices? Well, it depends. Like in a permanent implant, it's probably not that good of an idea because the biocompatibility risk is certainly very, very high since you have a very long and very invasive application. And then if you have something like a crutch, you have contact with in-contact skin, or even no patient contact because it's only the mechanical parts. And in that case, your biocompatibility is even not, the ISO 10993 might not even be applicable since you have no patient contact, or it's a much lower risk. And the key influencing factors, as I said, is like the invasiveness, the contact duration. And the third thing is going to be the raw material and manufacturing processes that go into here. So it's the extractable leachables, what kind of chemicals can leach out of the material, the surface chemistry and topology, but also particles and wear, and the chemical and biological stability. Then what's also very, very important is that the biological risk is always assessed on the final device in its finished and final form. So including sterilization and packaging. I'll make an example. So for example, we use POM, polyoxymethylene, which is a polymer that is very prevalent in MedTech. It's very good dimensional stability, very good tribological properties. But if you sterilize it too hard or if you process it wrong, you will release formaldehyde, since formaldehyde is the monomer of POM, meaning that it can be biocompatible if you process it right. However, the sterilization and manufacturing process can also release chemicals that might be not as good for your biocompatibility. So then it's also very important to assess this biocompatibility according to the intended use and patient contact. And newly, in the newest version of the ISO 10993-1 in 2025, it got an update. Now we also have to take into account reasonable foreseeable misuse. For example, if you have an anesthesia or like a breathing circuit that's only dedicated as a breathing circuit, you might also foreseeably see that this could be misused as an anesthesia circuit, and you'll have to be planning for that. Or you can also say, okay, this is for an adult, and then you could also reasonably foresee that this is used in children or for children. And therefore, you'll have to take into account those cases as well. And the biocompatibility risk assessment needs to be performed by a competent individual. How you really show that this individual is competent enough, usually you provide the CV and you provide relevant working experience and you provide relevant education. But the notified bodies will be looking at who has performed this analysis and is the person competent enough. So, biocompatibility as risk assessment or in risk assessment. Risk always is the probability plus the severity of the damage. So, how probable is it and how much damage does it do? And that is written down in the ISO 14971 framework. That is like the umbrella of risk management in medical devices. And the ISO 10993 very strongly follows this framework. So at the device level, we need to establish risk management. We need to establish risk analysis. So what could happen? Then we need to evaluate those risks. So what's the probability and the severity of those risks? Then we need to take measures, risk controls. So what do we do now about these risks? Or do we even need to do something about it? And then we need to analyze the residual risk. And sometimes we need to provide such justifications for that. And then in the end, we all have to document everything in the risk management file. And the biological risk assessment follows exactly this logic, and it is one input for the risk management file. Meaning we will analyze the biological risk. Okay, what could happen biologically if we have this device made out of these materials and manufactured in this way? Then we will evaluate, okay, what's the probability that this happens and how bad can it be, basically? So what's the severity? Then what do we do about this? We need the risk controls, and that could include biological testing. And then we will analyze the residual risk, and sometimes we will also provide justifications for that. And how does that in the end turn out? So the acceptance criteria for safe medical device, safe means free from unacceptable risk. And that's like the base principle in risk management, because zero risk is not possible. There's always a residual risk that something could happen. So the freeness of unacceptable risk is what safe means in a medical device context. And now, where does ISO 10993 come in? So ISO 10993 follows the before mentioned logic, and it deals with the biological risk in a 14971 framework. It requires that we identify the biological risks. We estimate what those risks are. We analyze existing data. This is very important. So we go and look, okay, these materials they could have certain leachables, or if we take the example from before, POM, we have the risk that we could have some formaldehyde. Doesn't mean that we have to exclude the material, but we need to understand if in this manufacturing process, in this application, it can be safely used without releasing too much formaldehyde so that a person is reasonably safe from unacceptable risk. And then we need to justify which tests we want to do, or if we do not have to test at all. And then we have to have an evidence-based conclusion on if the device is safe. So the key rule is always demonstrate biocompatibility via a documented risk management process, not by default testing. So we do not have a checklist approach. We just, okay, we have this device, we need to do this test. Now, this is not how it works. We need to gather the data. We need to understand our device. We need to make a risk assessment. And then if we have gaps in the data, we need to close those gaps via testing. That is how this works. And how should we do that? So we start with the existing data. So we gather data sheets, we gather formulations, if we can get them from the manufacturer. We gather certifications, historical uses of this material, sometimes literature, even sometimes they might have test reports. And then, if that's not enough, we start doing chemical characterization according to the ISO 10993-18. This is the chemical characterization part of the ISO 10993 series. And we perform this chemical analysis and quantify substances, extractables, leachables, in the materials and devices. And then what we do with this is, okay, this is what could come out of the material. And now we do a toxicological risk assessment, meaning we look at the concentration of each chemical coming out of the material or of the device. And then we make an assessment if this exposure to a patient would be critical or not. So what we do is we make a calculation of the margin of safety. And if the margin of safety is too low, further testing or risk controls are needed. If the margin of safety is above 1, it can be considered toxicologically safe. And then we would go for in vitro testing, something like a cytotox, something like an irritation testing, sensitization testing. Those are called the big 3 in biocompatibility testing. And if the device's use justifies or necessitates further testing, such as chronic toxicity or whatever, we can also go and do that. And then in the end, we will do in vivo animal testing. And the ISO 10993 also makes sure that we do the minimum animal testing possible. The ISO 10993-2 is about animal safety, and that you need to go through an ethics committee to get to animal testing. Good. So this is basically the core slide, which summarizes the biocompatibility process in general. This is quite the hefty one. So this is my approach to biocompatibility and how this is within a medical device development. So on the top, we have the concept phase, where we would rapidly iterate on our product. So here we would use our 11-step framework to eco-design, for example. We would rapidly iterate on the design, on the materials, on the concept. And at some points, we will have the design freeze, and then we start classic waterfall development. So we develop the device, then we industrialize the device, and then at some point we launch it. And then there's the post-market phase where it is on the market. And for biocompatibility, what you would do in the beginning is you would start with gathering data. Then you would do an initial risk assessment. Then you would do a chemical and biological testing phase. And then you have a final risk assessment. And then you would launch the device. And then you have a post-market surveillance phase and change management. So either the market gives you data, or you will have to change the device and reassess its safety. So in data gathering, what you would do is you will have your material recommendation. We call it the great match candidates, or the candidates that you would put into your material evaluation. You have the intended use, the body contact. Then you can also gather supplier data about these candidates. Then you have processing aid, auxiliary substances like printing ink or release agent on your mold. Then you have the contact duration and foreseeable misuse. So those are all inputs. And what you would need to do during this phase is you would have to request a lot of data from your suppliers. You would have to do literature research, and you have to do database research in order to identify substances of concern, red flags that could be an issue later. Because what we want to do at this phase is we want to identify red flag substances and red flag candidates as early as possible, so we can influence the material recommendation already, so that we don't run into the issue later. Because we take a material and send it to sampling and put it through all this development. We manufacture a tool, we set up industrialization efforts, we buy machines, all of that, which is customized towards one material. And then in the end, in the biological testing, it failed because of a substance of concern we could have spotted in this concept phase. That is what we want to do. We want to fail early. We want to find the substances of concern early in order not to run into the problem later. So we do a little more effort in the concept, in the material selection phase, and do not run into the problem later. Good. So how do you document this? You make a biological risk assessment for each and every iteration. So you start, you do a biological risk assessment, you gather data, then you have your iteration. If you're not happy with it, you reiterate, and all of the data that you gather during this iteration will find its place in the next iteration of your biological risk assessment. For those of you who are a little more advanced in biological risk assessment, it's the same approach that you will be using for a post-market phase or a change control phase. It's called the Lifecycle approach. If you're interested in how this is done, we of course have a full module on biocompatibility. So there's a link in the description, and then you can book a call with me and I'll explain everything to you. But that is it for the data gathering phase. This is the concept phase. And then when you have all your data that you need, you will do an initial risk assessment. So that is the evolution of this biological risk assessment by BRA. That will lead to a, let's say, full biological risk assessment. So you will have your recommendation at this point. You're sure, okay, it's going to be this material. You will have all the material information that you need for this. You have the manufacturing process, you have the sterilization method, you have the packaging. So that's an early development, I'd say, where you should have all of that finalized. You may be not having all of the tools and the final sampling, but you will have a lot of data that you need in order to do the biological risk assessment. And then when you did that biological risk assessment, there's a decision to be made. Is the risk acceptable or is it not? Do we need more data? Do we need more risk controls? What do we need to do? And if the risk is acceptable, oh, cool, you can skip all of the testing. So this is the number one learning from this video should be, it's like, sometimes you don't even need to test biocompatibility because you can infer from the data that you have that your device is going to be safe. However, usually this doesn't happen. So you always have some data gaps or some residual risk. So what you will do is you will do chemical characterization according to the 10993/18. And then you will do a toxicological risk assessment. And what you also usually do is big three. So cytotox, irritation, and sensitization testing. And with that, you would then have a pretty good understanding of your device. Sometimes it's necessary to have even in vivo tests, which you would do in parallel. And then when we have all this data gathered, we will put that into our final risk assessment, which is an updated version of this initial risk assessment. So of course, like these two, all this data and all the learnings we're going to put into the initial risk assessment, and then we have the final risk assessment. So here we have the finalized documentation of the risk and if it's justified. If it's unjustified, we need to loop back, we need to change the process, we need to change the material, or we need to do additional testing in order to justify all of this. But in the end, we will document everything, if also the risk is justified and how it's justified. And then we can finalize the risk documentation and say, okay, this device is free from unacceptable risk and we are safe. And then we launch it to the market. And then sometimes we will have a supplier change, we will have a material change, we will need to change the process, or we have a failed signal. So something unexpected happens with our device or with the device of a competitor made out of the same material. And that is what post-market surveillance is for. It's like we have to surveil the market and see, does something happen with our devices that we do not like? So we will have to adjust our risk measurements. And if that happens, we will have an impact assessment. So we will understand what happened. For example, we have a housing of an electronic medical device, has no patient contact or only occasional patient contact, and we need to change the colorant since the master batcher has changed the colorant from one cost number to the same cost number from another supplier. And in that case, we can probably safely say that this has no impact on the biocompatibility. But if you have an implantable device and you need to change the material or the manufacturing process, this of course has a very high impact and you will probably need to redo some of the testing. But you always make a risk assessment. And if your risk assessment says you need to do measures in order to justify the risk again, or that the risk is too high and we need to do some testing, we need to do some additional data gathering in order to understand the risk better, then we will do that. And according to our QMS system, we will have to update our documentation. So it not only can affect the biocompatibility testing, it can also be a kappa, for example. So it's a corrective action, preventive action. Something happens in a device, in one device with one material, but we have several other devices that are made of the same material. So we need to address those too. So this is a very rough overview over how the biocompatibility process works. I know it's very dense, but let's get to the conclusions on how to use this in a plastic selection situation. So number one is during the material selection phase, we should start with gathering supplier data as much as possible. So data sheets, safety data sheets, certifications. You should, if you're able to, get a formulation, understand what additives are used, what processing aids are used. Sometimes you'll even get biocompatibility testing reports from your suppliers. And you should use this evidence that is already existing to inform your biological risk assessment. And then you can also use something like substance information from ECHA or PubMed to understand what these substances in your devices are. Sometimes you can also run an ISO 10918, so an extractable leachable studies on your material in order to better understand what kind of leachables could be coming out of here. And this reduces uncertainty and provides an early risk signal. Then you perform on these substances that you have, these potential red flags, an ISO 10903-1 risk assessment during the prototyping phase. So very important, before you do the material recommendation, you run this. And that can in turn inform your grade match recommendation. So your recommendation of your plastic selection, basically. So you have the candidates, and then you have the recommendation. If you're not very aware of how plastic selection works, I think I have a video on it. Check that one out. And your biocompatibility risk assessment can then inform your recommendation. So what you will move on during the development phase. What you should also do is you should check for change control if it's needed in your application case. So if you have a more critical, more invasive, longer duration application, you should check for change control. Because if your grade does not have change control, or at least notification of change, that will be a problem, because you do the biocompatibility assessment on one lot and then the next lot is going to be void because you do not know if the lot is exactly the same. So this helps minimize the risk of failed tests later. So you do the work now, you understand the biocompatibility risks and the red flags now, and in a later stage, you will have a lower risk of failing a test or having problems in the market. That does mean minimize, not eliminate. It's very important. It's never possible to eliminate risks completely. You can only minimize them towards a degree where they are acceptable. And when you have done one of these biological risk assessments, you will, with every iteration of your concept, you will update it. So you use the so-called lifecycle approach to iterate during the concept phase. And with that, you have the best possible preparation for your biocompatibility testing and the best chances of not failing your biocompatibility tests. Good. So if you're a MedTech company and you want to understand plastic selection and sustainability, then there's a link in the description for you. You can click that and I would love to talk to you. And if you liked the video, like, comment, and subscribe, because YouTube likes those and you will be shown more of these videos. And if you want to request a video or have a questions towards what I just talked about, then you just comment and I read all the comments and I will promise to write you back. So thank you very much for watching, and until the next time.